Okay, hello everybody. Getting started with workshop number 6 here. Workshop 6 for physics. Today we're going to talk about collision and momentum. We're going to work some problems involving that. And as usual, before we get started, let's think of some of the core concepts involved. Let's write down any super necessary equations for some of the problems we're going to tackle, if any. The very core one to this whole principle, well, I would say there's two. The first one starts with just P is equal to mv. And here in this equation, P is momentum. You'll often see it also with the vector script over the V and with the vector script over the P. Let me see if I can put this more central to us. Okay. So we have momentum P, we have mass M, and we have velocity V. This is pretty intuitive. I think if you imagine something like a linebacker, right? You have this sense for how much momentum someone carries as they go to tackle into another player. And if they have a large mass, if they're a large player on the field, they carry a certain amount of momentum. And also if they're going very fast, if they're traveling faster, they also carry an increased amount of momentum. So we can see momentum is related to how much mass and the velocity that the mass is traveling at. Now, the next one that's super important for these collision problems is the idea of the conservation of momentum. The conservation of momentum, and it's similar to the idea that we've been working on, the conservation of energy. So you've probably seen in your class, you've seen that Pi is equal to Pf, which is to say the final momentum is the same as the initial momentum. No momentum is lost from the system, particularly when we're using this as in scenarios where you have one object or multiple objects. One object is colliding with another object, let's say. A billiard ball crashes into another billiard ball as we're playing pool. There's a collision, there's a transfer of momentum. Ultimately, no momentum is lost. So the momentum from before the collision is the same as the momentum directly after the collision. And we can use that principle to ascertain some information and solve lots of problems having to do with collisions, which would be pretty complicated and difficult to do if we were doing a force analysis like you've been doing using Newton's laws. Okay. So let's see, do we want to talk about anything else? Yes, we do. Because there's different kinds of collisions. There are different kinds of collisions. I'll propose two to you before we get started. So one of them, let's imagine. So here we have the Earth. And then hurtling towards the Earth is a meteor. When the meteor strikes the Earth, they're not going to bounce off and go their separate ways, right? The meteor is going to crash into the Earth, and it's essentially going to become part of the Earth. It's just going to get stuck in a crater, and it's just going to join in with the mass of the Earth. So this is a scenario in which the objects formerly were separate, and then they become combined. And we could also think of a different scenario where that doesn't happen, So you have the billiard balls is a good example. One billiard ball, it crashes into another, they kind of careen and they go in their separate directions, but they don't fuse together into one large billiard ball. They just bounce off each other and they go different ways. So what are these different kinds of collisions and what does it mean in terms of the math? Well, there are two that you want to know specifically. We'll reference this as we go. So there's an inelastic collision and an elastic collision. Let me see if I can post this up. Okay. So we have an inelastic collision is one for which the total kinetic energy of the system colliding particles is not conserved. A perfectly inelastic collision is one in which the colliding particles stick together after the collision. Oh, and so I should say that there's a third type of collision. Let me move this right here for classifying broadly. Let's see. The billiard balls, this is going to be the, okay. This is perfectly inelastic. They stick together. Perfect inelastic. So this is one where the energy is not conserved. So in the case where the energy is not conserved, we would have this equation to draw on. We could say that the momentum is conserved, but we couldn't say what we've previously said, which is that the initial energy is equal to the final energy, particularly that the kinetic energy initial equals kinetic energy final. Sometimes we'll use this equation in collisions, but we can't use it with certain types of collision. So with our perfectly inelastic collision, we don't have that conservation. We don't have that conservation. What's going on is the energy is going, it's leaking out of the system in other ways that are not kinetic energy. Namely, the meteor is fusing to the Earth, right? We know there's a tremendous amount of thermal energy that's released with this impact. And there's also a tremendous sound. There's like a big boom, right? So all of that is energy from this system that's now being lost and kind of leaking out of the system in other ways. If we were to do our LOL diagram, we would see the sound and the heat produced by this strike would be outside of our system. It would be essentially lost energy to us. And again, it's not lost to the universe. It's just lost to the local system that we're considering, these moving bodies. So we can't say the kinetic energy is conserved. In an elastic collision, though, this is one where the kinetic energy of the system is conserved. And really, this is an approximation, because in an elastic collision, these two, now if instead of billiard balls, we imagine particles, they kind of need to never touch. They kind of need to have this spring-type force between them. And it needs to be that they don't really actually collide, and there's no energy that goes anywhere else. There's no energy, there's no sound that gets made, there's no heat that is released. And because of this, the kinetic energy is conserved. The kinetic energy final is the kinetic energy initial. So this really doesn't happen on a macroscopic scale in real life, but it is sometimes a useful approximation. Sometimes it's approximately correct, and sometimes problems will tell you to assume an elastic collision. So if it's an elastic collision, we have both of these equations to draw from. We can use energy conservation and conservation of momentum. If it's some form of inelastic collision, we have the opposite. We can only say the momentum is conserved. All right, so now we're equipped to tackle these kinds of problems. Let's see what we can do. The first one, a 3 kilogram particle has a velocity of 3 in the I direction, minus 4 in the J direction, meters per second. Find its X and Y components of momentum. Find the magnitude and direction of its momentum. Okay, so this is as simple as we could start. The only trickiness here is that we're doing with vectors, so you gotta mind the vectors. They're just asking us what is this momentum vector P, right? They say find the X and Y components of the momentum. B, find the magnitude and direction of this momentum. So in components, we need to find this vector P. We know that P, the momentum, is equal to mv, v being the velocity. So really, we can just plug this in directly. What is m? They told us. M is 3 kilograms, 3.0 kg. What is the velocity? The velocity is a vector. It goes 3 in the x direction, comma, negative 4 in the y direction. And that's meters per second. That's velocity. So the momentum really is just 3 kilograms, 3 kg, times this vector quantity, 3.0 meters per second, comma, minus 4.00 meters per second. And you might also see the I's and J hats in here. You might see X's and Y hats, and that all means the same thing. We're just referencing the direction. I've chosen not to write them in here because I like the vector notation with the brackets and commas. But it's the same thing. I could have written it the other way. Let's see, that's not what I wanted. There we go. So these are axes. These are our axes. We would have our x-axis is right here. We would have our y-axis is right here. This is the direction of I hat toward the x-axis, and this is the direction of j hat. So if we were to travel 1, 2, 3 meters per second in the x direction, in that same amount of time, we would also be traveling 1, 2, 3, -4 meters per second in the y direction. So that gives us a vector that looks something like this. This is our velocity vector. That's our velocity vector. So now, if we go back to the math here, you know, if you're multiplying a scalar by a vector, you just multiply the scalar through against each component of the vector. So this just becomes 3 times 3 is 9.0, and this becomes kilograms meters per second, which is the unit of momentum. So looking good so far. And this becomes 4 times 3 is 12 kilogram meters per second. There we go. Doesn't get any easier than that. We're just following the definition right here, straight from the formula, the definition of momentum, calculating it through. Let's see what the next problem is. Okay, so this one says a 65 kilogram boy and his 4 kilogram sister, both wearing rollerblades, face each other at rest. The girl pushes the boy hard, sending him backward with a velocity of 2.9 meters per second toward the west. We can ignore friction. Describe the subsequent motion of the girl. Okay, so let's see the situation. If I can approximate it with maybe with stick figures. So here's going to be my boy right here. He's wearing his rollerblades. And here is going to be his sister. Okay. Now the sister gives a push to the boy. They're both wearing the rollerblades, and there's no friction being applied to them. So what can we say about what happens here? What can we say? We can say that the final momentum needs to be equal to the initial momentum. We can say that PI needs to equal to PF. So this comes from the idea that when you enact a force, there's an equal and opposite force that reacts back on you when you're contacting someone. So as the sister pushes her brother's body pushes back on her. She comes into contact with maybe his chest, and his chest pushes back on her hands in turn. So the force goes forth and back, and the momentum needs to be conserved. Now, initially, what is their momentum? They're sitting at rest. So let's look at the momentum of the girl. She has some mass. She has a mass of 40 kilograms. And what's her velocity? Her velocity is 0, right? So isn't her momentum 0? 40 times 0 is 0. Now let's look at the boy. He's got a mass of 65 kilograms, and like his sister, he is at rest. He's at rest. So his velocity, relative to maybe the skate rink or something like that, is also 0. Also 0. So his momentum is 0. So what is the initial momentum before the push occurs? Initially, there's no momentum whatsoever. Initially, there's no momentum. So we have that 0 is going to be equal to PF. Okay. Now, does that mean that nothing happens? Does that mean that there's no motion whatsoever? No, that's not what that means. It means that, remember, this is a vector quantity. It means that the momentum must cancel out such that it is equal to 0. We would expect the boy to be pushed in this direction. In fact, it says that he gets moved in this direction to the west left side of the screen, let's say, with 2.9 meters per second velocity. 2.9 meters per second velocity. So in order for the momentum to cancel out, it must be that the girl also slides back. And if you've ever thrown a heavy object or pushed something when you're on rollerblades, you know that this is what happens. Maybe you just push off the wall. So let's calculate this. Let's see how this goes. So what is the final momentum composed of? Well, in our system right here, we're concerned about these two moving bodies, So one is the boy. He has a mass of m, it's going to be 65 kilograms. And he has that velocity that they told us. I'll just say v boy, vb. All right. Okay. And the total momentum, the total final momentum, is the sum of the momentum of all the objects in our system, all the objects we're considering. So the mass of the girl multiplied by her velocity, v girl, v sister. I'll put a G. Okay, and then the sum of all of that should be equal to 0 because initially there was no momentum. So if we're going to make momentum, we can't just make it out of thin air. There has to be an equal and opposite response, right? This is not always obvious when we're on the ground, when we're on Earth. There's lots of other forces at play. But if you're in space, this becomes very plainly obvious. If you're just floating freely in space, and you send something away from you, then you pushing on that thing and sending it away from you pushes on you back and it sends you back. It's the same conservation of momentum. And this is happening all the time on Earth, and you can test it out. It's especially easy to do when there's something like friction is not there, when you're on rollerblades or when you're on ice. When the friction is holding you to the ground, it doesn't become as obvious. You feel that you are kind of thrown back by your push, but you may not actually move because you kind of hold yourself to the ground, thanks to friction, thanks to some other things, helping you stay in place. For this scenario, let's just see what's really going on here in terms of the momentum. So it must be that the girl goes in the opposite direction. That's the only way that these are going to cancel out. They have their two different masses. And what did they ask us? They said, describe the subsequent motion of the girl. So as I'm thinking about it, I know it must be in the opposite direction in order for the final momentum to be equal to the initial momentum, which is 0. Somehow the sum of these needs to be 0, right? Or in other words, we could say that MVB needs to be equal to negative M, and then this really should be mg. I'm kind of distinguishing it with color, and this should be mb. They have different masses. Apologies. This is vg. Okay. Okay. So what do we want to do? We want to solve for v girl. So we can solve for this velocity, right? So we're just going to divide their masses, the ratio of their masses, multiplied by the velocity of the boy. So we get mb times vb divided by, let's say, negative the velocity, negative the mass of the girl, and that will enable us to solve for the velocity. Okay. That gives us on this right-hand side, we just have VG. Let me punch that into my calculator real quick. Let's see what we get. So we're taking the mass of the boy is 65 kilograms, and I'm going to divide that by 40. So that's 65 over 40, multiplied by 2.9 meters per second. What does that give me? That gives me a velocity of 4.7. This gives me equals, I'm going to round, it's 4.7125. I'm going to say 4.7 meters per second. Okay, and we know that this is, I'm sorry, it's negative. That's because it's in the opposite direction. It's in the opposite direction of west. So we can say this is a velocity to the east, or we can say it's negative to the west, whatever you want, doesn't matter. And we've described the motion of the girl. We have this velocity vector. So if I want to say it really clearly, let's just put 4.7 meters per second eastward. Okay. And does this make sense? Does this answer make sense? The sister is going faster than the boy. And that's what we should expect because she weighs less. She has less mass, right? She is lighter. So if we apply the same force to the boy and to the girl, we would expect different accelerations. Or it's easier, in other words, to change the speed of the sister than it is to change the speed of the boy, to change their velocities, That is exactly what we would expect. Let's take a look at the next one. Okay. Okay, and I should say, okay. Well, I'll talk about it on this next one. So we have, in this one, it says, number 3, a 10-kilogram bullet is fired into a stationary block of wood. The block of wood weighs 5 kilograms. The bullet embeds itself into the block. The bullet embeds into the block. This is giving us a hint about what kind of collision it is. Let's underline the important information. You guys will practice picking these out. And then when you do harder problems, you have to pick out these same keywords and help put it together. The speed of the bullet plus the wood combination immediately after the collision is 0.6 meters per second. What was the original speed of the bullet? So the bullet embeds into the block. This is telling us how the collision takes place. So this tells us that it's a what kind of collision, Let's scroll up. Let's think about our types of collisions. Oh, did I not draw this one? Did I not draw this? So this was the elastic collision. They bounce off of each other. Perfectly elastic. And then this is the inelastic collision. In which they still separate. They don't necessarily stick together. However, there's no loss of energy. It's not like, I'm sorry, there is loss of energy. It's not like the elastic in which there is no loss of energy. I muddled that up. Let me try to be clear. So if we don't have a perfectly elastic collision, this elastic collision, if it's not elastic, then what does that mean? That means the kinetic energy is not conserved. We cannot use this formula. In the elastic collision, we preserve our kinetic energy. We preserve the energy of the system because the energy doesn't transform into other forms of energy. There's no sound from the collision. There's no heat transfer from any friction of the objects colliding and crashing and smushing against each other, etc. So in the inelastic collision, this is not the case. We hear the crash, we hear a sound. This will be the case for most all things. Like I said, this is kind of an approximation. But what do they tell us about problem number 3? They said that it embeds itself. And I said that if something crashes and then sticks in to an object, it stays with it and it kind of becomes part of the same object, becomes part of the same mass. That would be a perfectly inelastic collision. And in an inelastic collision, the kinetic energy is not conserved. So the bullet is fired into a stationary block of wood. The bullet is a mass of 10 grams. M equals 10 grams. Okay. All right. And the wood block, I'm going to call that big M. And I'm going to say that's 5 kilograms. Okay. 5 kg. All right. Okay. And then we have the collision time. Oh, so the speed after the collision, not the collision time. After the collision, the speed of the bullet is 0.6 meters per second. So VF is equal to 0.6 meters per second. Okay, now let's look at this. We've got our core equation. You remember it. It's that the initial momentum is equal to the final momentum. Let's try and give this a solve. So what is the initial momentum? Well, we got to look at the whole system. What we have is a bullet. Here's my attempt at a bullet. It's looking something like that. And it's speeding towards, at some unknown speed, a large block of wood. Okay. This is time 1. This is the initial frame. And then in the final frame, the bullet has struck the block of wood. It's gone some ways into it, maybe. It's kind of embedded itself into the block of wood. And now the block of wood is kind of sliding after the force it received, this momentum that collided into it. So there's the final frame. So in the initial frame, there's 2 objects, right? We've got the block of wood, and it has some momentum associated with it. And there's the bullet, and it has some momentum associated with it. So let's break that down. So we have little m as the bullet, and we have the speed of the bullet. So let's say VB for V bullet. Okay. And then in addition to that, we've got the momentum of the block of wood. So P is equal to M times V. So this is big M for the block of wood. And what is its velocity? A stationary block of wood. A stationary block of wood. Velocity is 0. So this M times 0 is 0. And this just goes away. And this just goes away. In this problem, at least. Now, in the final scenario, what happens? It's moving now with some VF that they told us was 0.6 meters. Well, what is the mass? This is a perfectly inelastic collision. The masses have combined. Now we're looking at this one object, and it has the mass of the block, obviously, but it also gained the mass of the bullet. Now the mass of the bullet is attached. So now the mass, when we say P equals mv, now this mass that we're talking about is their combined mass. Because that whole mass is moving together as a unit. That whole mass is moving together as a unit. So this m really becomes m plus m. That times v. And this is vf. Okay. And what did the problem ask for us to do? It wants for us to solve for VB. So I think we can do that. This is a 0 right here. We know what m is. We know what little m is. They told us VF, so we know what that is. And once again, we know what little m is. So if we have one equation and one unknown, we can solve. If we have one equation, one unknown, we can solve. And these problems, I like thinking about the number of unknowns and the number of equations, because a lot of times you'll have multiple equations. It could be that we had a kinetic energy equation in here. Maybe they were asking us to solve for 2 unknowns or more unknowns. So it's a good reminder to yourself. How many equations do I have? How many unknowns are there? And if you check and you go through and I have equations equal to unknowns, then you're ready to solve. If not, you got to keep working. You got to try to find something in terms of something else maybe. Okay, but yes, we have one unknown and we have one equation, so we can solve. So we just have to isolate VB, your basic algebra. So let's get VB alone. We're going to divide the left-hand side by m. And here we just end up with m plus m times VF divided by m, little m, for the bullet, is going to be equal to VB. That was the speed that the bullet was initially traveling at. Let me punch this into my calculator. Let's see what we get. Okay. So we have the block is 5 kilograms. And I should say, before we punch this into our calculator, we need to do a little conversion here, right? They told us this is 10 grams. We really want that in kilograms. We really want that in kilograms. So 1 gram is 1/1000th of a kilogram. 1/1000th of a kilogram. Okay. Punching this into the calculator. Sorry, I made a little typo. Repunching it. Okay. All right. So I have a speed of 300.6 meters per second. Meters per second. It's quite high. Let's see. I'm going to convert that to miles per hour in just a second to see where my answer is coming in at. So 300 meters per second is about 670 miles per hour, approximately 670 miles per hour. I think that sounds a little slow for a bullet, but is pretty reasonable. MPH. I think that's pretty reasonable. Now this problem is kind of interesting to me. I quite like it. So the mass of the bullet is very small, but its velocity is very great. So the combination of that ends up with a kind of significant momentum. Then the mass of the block is very great, whereas the velocity of the bullet block mass combined ends up being very small. So that large amount of momentum, or relatively sizable amount of momentum, depending on what you're comparing it to, becomes kind of a pretty small factor in the overall block system. And yeah, a bullet travels tremendously fast, but it's so small, it doesn't carry so much momentum. It's not like if you've ever seen movies where people get shot and they go flying. Well, that's not what happens. It doesn't have that kind of momentum. Okay, so we've solved number 3. Let's go on to number 4. And we'll do one more. Ooh, if we have time. I'm always running out of time. 2 automobiles of equal mass approach an intersection. One vehicle is traveling with a velocity of 13 meters per second to the east. The other is traveling with a speed of v2i. Okay. Neither driver sees the other. The vehicles collide in the intersection and stick together, leaving parallel skid marks at an angle of 55 degrees north of east. The speed limit for both roads is 35 miles an hour, and the driver, okay, all right. And the driver of the northward moving vehicle claims he was within the speed limit when the collision occurred. Is he telling the truth? Explain your reasoning. Ah, interesting. Okay, so this is kind of qualitative, although we may need to get into the math to answer it definitively. So let's take a look at the situation. I'm going to draw it real quick. Okay. All right. So here we have car 1, this automobile. They have the exact same mass. Did I read that right? The 2 automobiles of equal mass. Okay, of equal mass. It simplifies things a little bit. So we're traveling 13 miles. Oh, so I'm sorry, 13 meters per second, they tell us. 13 meters per second toward the east. And the other is traveling north with a speed of v2i. So that's some unknown speed, which we're going to call v2 initial. Let's do another arrow for that one. So due north, and then they're going to crash into each other. Let me do a straighter arrow than that. So they're going to collide at an intersection, right? This one is traveling due north at speed of, I did want that to be red, at speed, unknown speed, V2 initial. Okay. And the driver of the second car claims that he was traveling under 35 miles per hour, under 35 miles per hour. And we're to determine whether or not that's true. Whether or not that's true. Okay, I've been forgetting to encourage you to pause and think about it and try to solve it on your own, but you should definitely do that. Give it a go. Don't just watch me solve it. Just use me for hints if you get stuck, and use me as little as possible. Let me try and drag this down so we have some more space. So I want to kind of continue this drawing. Okay, so now you've tried it, and you probably solved it all on your own, but you want to see maybe how I approach it. Sure, let's do it. Let me go back to draw. So now it tells us if this is east, the two cars stick together. Ah, a hint. This is a what kind of collision? What kind of collision? Go back and review if you don't recall. Perfectly inelastic. And they launch off at this angle. Let me do this. It's going to be the resultant vector. Do it in blue. Okay. And the angle is 55 degrees. Let me make sure that I got that right. Got to make sure we set up our problems right. 55 degrees north, 55 degrees north of the east. So this is east in our drawing. Okay. Here's east. This is due north, west, so on and so forth. Yada, yada. So this is their new trajectory. This is their new direction that they're traveling after the collision. So what's happened is the one car was traveling due east, the other car was traveling due north, and now their combined velocity is sort of in this northeasterly direction. Okay, let's go qualitative before we get into the math, and let's think about what this means. So if the momentum of the northward traveling car had been overwhelming, right, compared to this car traveling to the east, then it would basically, like if this was a semi truck traveling at 60 miles an hour, and this was just like, I don't know, say a toy car, then the toy car would just get flung off in the direction that the momentum of the truck was going, and the truck would just kind of keep going about its way, right? It would be unaffected. But since their masses are kind of similar, in fact, they're equal, and their speeds are maybe comparable, they end up kind of launching off at an angle. So their new velocity becomes a combination of their two former velocities. And we just discussed how if one of them was really insignificant in terms of momentum compared to the other, it's kind of like a battle between them. It's kind of like a battle. They would just keep going north. Or if this one was really the more significant with momentum, they would keep going east. But they're really kind of off to an angle, right? But they're not in a perfectly equal angle between them, right? They don't come off at a 45. If they came off at a 45-degree angle, then it would be that their combined velocities are basically equally to the east and equally to the north. But this is 55 degrees north of east. So are we traveling more easterly overall, or are we traveling more northerly? We're traveling more towards the north, right? So this car, since it has the same mass, it must have been going faster than this car, the 13 meters per second. Now we could break this up in a vector analysis, right? You guys have done this before in your class, I think. And we can look at the x components and we can look at the y components. And maybe we can answer exactly Maybe we could answer exactly how fast this v2i is. But let's see, it says explain your reasoning. We're reasoning through it. So let's see, maybe can we come to the answer just by doing this reasoning. So I've reasoned out why I think that this car must have been traveling faster than 13 meters per second because it won the battle. Its momentum carried forward and is more dominant in the overall velocity of the new vehicle, is more dominant than the overall velocity of the new vehicle. So what is 13 meters per second in miles per hour? 13 meters per second in miles per hour is about 30 miles per hour. So this is about 30 mph. So I don't think it's looking good for our guy. I don't think it's looking good for our guy. I don't think that he's probably telling the truth because this guy was already going 30 miles an hour and we had to be going somewhat faster than that in order to, if we were also going 30 miles an hour under the speed limit, then we would go off at a 45-degree angle because our cars have the same mass. Our cars have the same mass. If we were going slower, if we were going 20 miles an hour, then we would be at less than a 45-degree angle. We would get pushed more to the east than we did to the north. Well, that's not what's happening here. Now, it's a little unclear. We're not for sure, right, that he's over 35 miles an hour. So I think we can do the math a little bit more. I would encourage you to do that and solve this through. I'm just about running out of time. Should I do this? Yeah, let me at least. So you've had a go at it. You've tried it maybe. Let's see if we wanted to be sure what would we do. So we're curious about what is the ratio between this that is VFY and VFX. Okay, I'll just set this up. We won't finish. So the tangent of theta relates those sides. It relates the opposite to the adjacent, which in this problem is the same as it relates VFY, the upward component of the final velocity, to VFX, the easterly component, or the right ways component of the final velocity. So based on this ratio, if we put in a tan of 55 degrees here, what do we get? Let me see here. Tangent 55 degrees, make sure you're in degree mode. I get about 1.4, Where's my pen? There it is. So tan of 55 is up about 1.4. Let's say I'll say approximately 1.43. All right, that's plenty of enough detail. Okay. So now we can set this up. Now we can say PI equals PF. Okay. We can look at, on the one hand side, what do we have? We have the vehicle one traveling in the right direction. So we have the mass is just m. It's the same mass. We have the 13 meters per second to the east, 13 ms east. Okay. I'm going to call that I hat. Rightward. Okay. And then in addition, initially we had the car traveling to the north at V2I, the mysterious V2I that we don't know. Okay. And that's to the north. So that's J hat. And that needs to be equal to the final momentum. They stick together. So this is M plus M, right? Their combined mass. Or can I just call that? Do you guys mind if I just say 2M, right? M plus M, 2M, 2 times M. Okay, times the velocity that is the combination of VF. This is times VFY plus VFX, right? If we sum these vectors together, the X direction and the Y direction, we're going to get the resultant vector, which is the blue vector here in my drawing. And now, what would we do? I'm out of time, but we would solve for this. Can we do it? We're trying to solve for V2I. Well, we don't know this directly, but we do know the ratio of how these relate one to another, So we can say that VFY is 1.4 VFX, right? Let's see if that checks out. Tan 55. So this is 1.43, I said, is equal to VFY over VFX. Multiply both sides by VFX. We get 1.43 VFX is equal to VFY. So this tells us exactly, based on this 55-degree angle, how much more are we traveling in the y direction than the x direction? Well, the velocity is 1.43 times as much. 1.43 times as much. We can plug that in here. And I think the answer is getting clearer, as we say, but we can solve this directly. I encourage you to do that. I'm unfortunately out of time. But you can go through this math here. It's pretty straightforward. We can see the masses cancel out. Okay, I'm tempted to keep working on it, but no, I've got to go. All right, I'm packing up. But we've studied over momentum and collisions. You learned that our key equations for analyzing these collision type problems are the definition of momentum, mass times velocity, and the conservation principle of momentum, the principle that momentum is conserved. We learned that there's two basic types of collisions you need to consider. There's the inelastic and the elastic collision. In the inelastic case, the kinetic energy is not conserved. In the elastic case, the kinetic energy for the system is conserved. And there's also this perfectly inelastic case, which is where the objects combine together. And the only thing special about that case is then you have to combine their masses. You have to consider their combined masses in the final or the initial or whatever frame it's working, depending on the problem. We solved several different problems working with these techniques, and I think you're ready to tackle even more difficult ones. Thank you. I hope you found this useful.